record on this computer. It's recording, but I still can't manage to get this window out of the way. This window down here. All right, not great. So we should be recording now. Is there some evidence of that? Yes, okay, good. Thank you. All right. So, so final review is here. Overview format, similar to the midterm format. These are the topics we covered. Here's a link to pre-midterm. There'll probably be at least one question that is a pre-midterm question. Probably almost surely be write a Scala function. It's a combinator, takes a list of functions and converts them into some different kind of function, something of that nature. And then sample questions. We have environment diagrams. Here's a Jedi programming so this is a pre-midterm kind of thing. Jedi program. Here's another Jedi program. Oh wait, is this the final review? There's something funny about this. This list of questions, okay, I'm gonna have to maybe fix this. This list of questions sample questions seem like mostly midterm kind of questions. I know enhancing Jedi, that's a post-midterm. Jedi programming, so I'm doing what you're gonna do on the final. I'm getting Jedi and Scala mixed up. Yeah, so this is all, there are a bunch of Jedi kind of questions here. So Jedi is like post-midterm, parsing, that sort of thing. So we'll get into that, and I'll try to update that final review a little bit before Thursday. Right, so then on the assignments front, we have Jedi 3.0, which includes Jedi 2 and Jedi 2.1. And let's see, its due date is, what's today? Today is Tuesday. When is this thing due? I know you know, but I don't trust you. Tonight, I think. Yeah, I think he's right. May 5th, yes. It's due tonight. So, so I guess the question is, so I had a couple of you in my office hours. So maybe what I cothe do is like at least start today by fielding any questions about the homework that's due tonight. So how are we doing on the homework? So hopefully you're just doing touch-up kind of things for the homework. Well, let me say like a few words about the homework. Let's take, for instance, I gotta bring you with me, don't I? Let me just say a few words about the homework and maybe that'll stimulate some discussion about it. If not, we'll move on. So we're skipping stores, doing iteration, variables, so forth. We're not going to have store in here. Here's iteration, an assignment, our special forms. Now, let's see, have I given you any hints about this? Not really. So a few things about iteration and assignments, and this is generally true of all special forms. You know, when you do a fun call, okay, when you do a fun call, if that function call is a built-in function, an ALU function, so that goes to the ALU, and the ALU does type checking there. So the ALU does lots of type checking. Let's see. Yeah, Samija, you're having, is that, I'll check that out, Samija. I'd be surprised if that was my fault, but I'll check it out in a minute. But the case with special forms is that you have to do type checking there. So, for example, assignment. Let's talk about, no, not assignment, iteration. Let's talk about executing an iteration. Okay, so let me bring up a new window here. All right, so right, so iteration, right? So what are you going to have? You'll have a case class iteration. All of your classes in the expression hierarchy should be case classes. An iteration has what? It has, it's probably going to have a condition, an expression, and it's probably going to have body, which is an expression, and it's going to extend special. And then see, I'm going to save this, not for any particular reason, but because put it in here. Save it as a Java file, just because then you get formatting. Oh, but it's going to turn the font back down again. Figure out how this text processor works. This text editor works. Okay, and so then you need, of course, you need to define execute. It's an environment. And so this is what I wanted to say here. Of course, execute, always returns a value. Okay, and so then here's the point that I wanted to make. Inside of execute, you're going to be executing condition. All right, so you're going to be doing something like while this way. You'd have something like maybe I don't know, something like this. So, and then you'll have while on is true, blah, blah, blah. And then you're going to return some sort of notification. Something like that. I'm just being very sketchy here. Here's the point that I wanted to make, though. You're going to have to execute the condition, right? So you might have Now, it's right here, what you've got to do is say, if it's not the case that res is instance of bool, you got to do something like that. You've got to do your own type checking inside of the execute method of nearly all of the special forms, right? Because these are not going to go to the ALU, so there's not going to be any type checking here. I believe this is instance of, I don't remember exactly what it is in Scala, instance of. So, so if it's not, I think it's, sorry, I'm getting mixed up because of, I'm teaching 151, and that's all, that's all Java stuff, right? And then, of course, your condition, you have to now you can safely cast it to, oh, Jesus, again with the Java. And again, I'm not being sort of slipshod here. I should look all of this up, but you all get what I mean here. So, and maybe we could even do R. And so, so now you can safely, let's see, no, I'm sorry, putting it in the wrong place. Slow down. Okay, so now you've checked to make sure it is a bool. If it wasn't a bool, the thing ended when you threw the exception. Otherwise, you can safely cast it as a bool. And now that it's a bool, you can extract out its Boolean value. So when I say bool, I'm talking about Jedi type, and Boolean, I'm talking about a Scala type. Because what has to go here is a Scala Boolean. Okay, and so then, what this says is, remember the kind of expression here, it looks like this, while condition. So I've said this a million times before, but I like to say it again. So what we're saying here, the whole point of an interpreter, a reference interpreter, this is sometimes called a reference interpreter, is that we're trying to specify the semantics of a new language. Semantics, it's a big word. Behavior is maybe a simpler version of it. How certain expressions in this new language behave. We specify the syntax. Syntax, another big word, means structure. We specify the structure of an expression by using a grammar rule. Right, so in this case, it would be iteration while followed by a parentheses, followed by an expression, followed by another parentheses, followed by another expression. This rule here tells you the correct syntax, the correct structure of a while expression. And then this execute method here is telling us the correct semantics or behavior of this thing. And reference interpreter means that we're to understand this as a specification, not necessarily as some super efficient production kind of interpreter that you would use. There we might be adding all kinds of hacks in there to just make it super fast. The purpose of this is to document, how, the syntax and semantics of while. And then the thing that's interesting here is that we're saying, okay, Well, I'm trying to tell you what this means in Jedi. And look what it boils down to after I fool around with type checking and casting and so forth, is a while expression in Scala. So basically what I'm saying is while in Jedi means pretty much the same thing as while in Scala. And remember, the game we're playing here is that you understand the Scala language, that's our meta language, but then I'm trying to explain to you the Jedi language, which is our object language. Anyway, so it's a long thing, I apologize. The point of it is, in these special form subclasses, do type checking. You know, something that the grader and I will be looking for. Okay. So some of you are having trouble with the web page. God, I hope that's not messed up. Let's see. So Jedi 2, I haven't touched it in a while here. Here's Jedi 2.1. Uh-oh. What? How did that get broken? Okay, let's see here if I can quickly fix that. This is in projects. I can try to reload the page. And then here we have you guys go over here. Okay, so just reloaded it. Now let's see if I reload this page. Does that fix it? Okay, Samija, maybe you can verify that the diagrams are back in there for me. Yay, thank you. I have no idea what happened. I mean, I don't think I've touched that area for a long, long time. So, these are strange, mysterious things. Okay. So I think, I'm hoping that your lack of questions means that you're all doing fine, and the homework will be ready tonight. We talked last time about adding objects to Jedi, and here we're not so focused on the implementation, just sketching the implementation. This was like kind of the new syntax. So I introduced an object operation expression. It's an object followed by a block, okay? And this block here creates a, this block here creates a temporary, just like when you execute a block, we create a temporary environment. We execute all of these expressions in that temporary environment. But the difference is the temporary environment is the output of this thing. So really what an object is internally is it's an environment that's being treated like a value. And we're also taking advantage of the fact that an environment can extend another environment. We add this extends operation here. So here I'm creating an object that extends another object. So when I add, I also have to add this qualifying notation, this dot notation. That's actually the hardest part of it. if it can't find, for example, it can't find anything define a balanced definition in here, it just naturally goes and looks in the extending environment here. So it's actually pretty easy to add objects. And then for constructors, we create these. I mean, it's just all, we already have it, right? Constructor is represented as a method that creates and returns a new object in design pattern languages are called factory methods. Our constructors are just ordinary functions that inside the function, they create an object, and the parameters of the function just specify initial values for the variables. Okay, so so that was pretty easy to do. The hardest part, like I said, is the parser here, figuring out how to parse that dot notation. So then finally, the final feature here is let's go to Jedi 5. And so I want, this is a lot of big ideas here. What Jedi 4 is missing that Scala has is static type checking. Okay, now static type checking, we'll see exactly what that means in a minute. Right now, dynamic type checking is what we're doing in Jedi 4. What that means is just what I started talking about at the beginning of the lecture. You know, while we're executing the expression, we are also doing type checking. So execution and type checking are intertwined with each other. Okay, and the disadvantage of dynamic type checking is that that expression that we're executing could be like an expression that's controlling the controlling the navigation system of like a SpaceX rocket ship, let's say. Okay, and it could be that, I don't know, maybe the gyroscope's at just a certain angle, and so we're going to be executing a path through this code we haven't executed before, and we're going to hit this type error, and we're going to throw a type exception. Well, it's too late, right? I mean, this rocket ship is already in the ionosphere, and now it's throwing an exception. It's like the program, this is a runtime error. Throwing an exception is called a runtime error, right? And there's no chance of recovering from it if the thing's up there. And so, we've just lost another rocket ship. And I mentioned that example because, and I think I told you this story before, back in the early days, of the space race between, the Soviet Union and the United States. They were ahead of us. And, we kept launching these missiles, these rockets, and from Cape Canaveral, it was called then, and I guess it's called that now too. And there were big TV events, like the whole nation would be watching. They were just tests, right? And these things would like get off the ground 20 feet and then explode, right? So it was very embarrassing. And one of them famously blew up because of exactly this kind of a type error. The control code was written in Fortran, which had dynamic type checking at the time. And so that was an actual real example. Here's a demo session of Jedi 4.0, Jedi 5.0. So I'm typing in 3 + 2, and I get 2 outputs here. First, it tells me the type. This is exactly what Scala does. And then it tells me the value. Okay. Here I'm defining a function, foo, and you'll notice something different here about this. So the parameter list for foo, I have to specify the types of the parameters. Okay, so this is the one concession that we need to make in order to get static type checking. Okay, so now this is just a definition. So the value produced by this is going to be okay. And the type of that value is notification. All right. Next, I'm curious to know what foo is. So I just type in foo. Okay, and here is the type. And look at this cool type expression here. This is called a type expression. Okay, this is the type. The arrows is similar to what we see in Scala. The arrow means it's a function. To the left of the arrow is the domain of the function, which is pairs of real numbers, which is exactly what we see here. And to the right is the range of the function. Well, if you took two reals, x and y, and you computed x times x plus y, the answer would be a real number again. And then here's the value, which is going to be a closure. That's what foo is. It's a closure. I don't have any good way of printing out closures. Neither does Scala. Here I'm defining point, which is an object. It's a notification. Okay, and now I type in point. And here we see a type expression representing point. This is kind of a weird type expression. It's sometimes called a records type or a class type, an interface type. So basically I've got curly braces around it. It's the type of all things that have two fields. First field is called XC and it's a type real, and the second field is YC, it's a type real. Here I'm typing in var, and the type is var of hello. And the type is, so this type expression means a variable that contains a chars. And then here's the value, which is hello. So one thing that you have to, I guess, appreciate here is that, first of all, the type checking is happening before the execution. The execution is what gives us the value, and the type checking is what gives us the type. So that's what makes it static. We do the type checking before we do the execution. The second thing that's kind of cool is that, well, when I tell you what the type is, I mean, sometimes the type is easy. It's something like integer or notification. Okay, but sometimes the type is a more complicated type, like a function type. So I have to have a special kind of a brand new language instead of expressions, type expressions. And type expressions are built out of primitive types using operators like parentheses for tuples, arrows for functions. There's curly braces for object types. Here's square braces for variable types. So I have a whole language of type expressions. So here is the execute that's in the console class. Okay, so remember console, we have the read execute print loop, prints a prompt, reads an expression in just as a string, and then it passes that string to this execute inside the console. It's not expression execute, it's executing strings. He's going to parse the string to get some kind of a tree, extracts from the tree an expression. So exp here comes from the tree, that's an expression. That's what our parsers do, right? They convert strings into expressions. Next, we're going to add a brand new method to the expression hierarchy called getType. GetType takes the global environment as an input and it returns a type. Okay, and this type, here's where we're going to print out the type. And then here, one of the types that we have is called the fail type. Okay, fail type means there was a problem somewhere, right? And so here is where we're going to throw our type exception. Okay, we don't need to do type checking in execute anymore because it's happening here, right? And notice then here is where we execute the thing. This is where we execute the expression. So getting the type, which could return a failure type if there is an error in it, is done here. And then later on, execution is done here. And that result goes back to the read, execute, print loop, which displays it. Okay, so this is really getting down to the nitty-gritty of static type checking. First, we do type checking, and we throw an exception if there is a problem, and then we never get to execution. Okay, so that's done first. And we'll get, I'll say a few words later on about get type, but it's funny, one way to think about this is that get type is kind of, it's kind of the little brother of execute. So when you look at the code for get type, every expression will have a get type in it. And get type will, instead of producing a value for you like execute does, I print a set of values for you. The type that if I had computed the value, this is the type that value would belong to. So it's kind of, it's kind of like execute, but at a higher level of abstraction. This is information about how we're going to do this. Now here I have type. I put type in the value hierarchy. That's questionable. You could have like a whole separate hierarchy for type. But every value has an associated type, is the thing, right? And here is primitive type. So in here, the primitive types, you're going to have things like integer, real, and so forth. Variable type, function type. Here we see some of the, just a little bit of code here. So here is type, it's a trait, and it has a get type function in it. Value, here is value. Value is getting redefined. It has a get type, okay, that returns the type of a value. And if it's just a value, then its type is value. Here is by class primitive type. Primitive type has a name, which is a string. It extends type, and it also can be treated as a literal. Okay, and then here is a list of the primitive types. So this is in a companion object, right? And here, for example, integer is the primitive type integer. So like with 3, if you ask get 3.get type, what's the type of 3? It's going to return this integer here. Here's the failure type down here. Here is the function type. It extends type, we see here, and it's got a domain, which is a list of types, and a range, which is just a type by itself. And here's a variable type. It's got a content type. So I hope you can see here that this is very much mimicking what we did in the value hierarchy. So the type hierarchy is mimicking the value hierarchy, but at a more generalized, abstract level. Okay, so then the way that type checking is done in modern languages is by using a kind of an artificial intelligence technique called type inference. Okay, and let's see, where do I want to go with this? Oh, let's see, we're not quite there yet. So here's the redefinition of the expression trait. So expression knows how to execute itself. And it also knows, given an environment, it knows how to tell you what type of value it produces. Okay, and I've given a default implementation here. I don't know what type this produces, but I can tell you that the type of value will be a value type. Okay, so you would override both of these functions. You have to go back through all of your expression classes, and you're going to have to put in a get type for each one of these things. And instead of returning a primitive type, right, you'd override this and give like a more definite answer there, like primitive type dot real or whatever it is. And then the goal of type checking is to ensure what's called type consistency. And here is type consistency right here. If you take an expression and you execute it in an environment, and then you ask what the type is, here's this parentheses in the wrong place, it is, shoot. You ask what the type of that, remember that this guy produces a value, and then we're getting the type of that value. So maybe it produces the value 42, and the type of that value is integer. You get the same thing as if you get the type, take the expression called get type, and this dot type here I think is a typo. So that shouldn't be there. So in other words, if we execute an expression, convert it into a value and say, what's the type of this value? You get the same answer as if we took the expression and we just called the get type function. Okay, so that is what we mean by type consistency, right? Both of those are the same. So on to type inference. So how is get type implemented? So we won't go into the details here, but just to give you a flavor of it, it's kind of cool. So type systems have a lot in common with logic systems. Like think about Euclid's system of axioms for geometry. Okay, so there are like axioms and rules. Okay, and the rules all have the form consequence if condition. Okay, and so we write down these rules and then we build an inference engine that can use these rules, and given an expression, it tries to deduce what the type of that expression is using these rules of logic. One of the things that I regret, I haven't gotten to this in a long time now in 152, but we used to do Prolog, right? Prolog is the logic programming. It's another paradigm we didn't get to. So Prolog does exactly this. So let's look at a couple of these rules just so you can get a flavor of what they're like. So f of x, what is that? That's a fun call. Now I want to get the type of this fun call, and it will be equal to r. Okay, so get type of a fun call is equal to r if get type of the function is a function with domain D and range R, and get type of X is D. Okay, so you see what this is saying? If you have a function of type D maps to R, and you have an input X of type D, then f of X will be of type R. Okay? Let's look at another one. So here is the conclusion. So this expression is defining a function. X is of type D and the body Y. If you get the type of this expression, it will be equal to a function with domain D and range R. We already see here that X is of type D, that's the domain. If when you get the type of Y in an environment extended by the assumption that X is of type D, then you'll get R. Okay, so what it's saying then in short is when you write down a lambda like this, this has type function that maps from D to R if Y has type R. Here's another one. Here's an expression. It looks like I'm dereferencing a variable here, and its type is T. If the type of V is a variable of type T. Here is add, so this is more complicated. Add, getting the type of this. This is a union type, okay, because there are 3 add functions: integer to integer, real to real, and chars to chars. And so you can take types and you can union them together. So those are, so you write down these rules, and all of these rules, basically what we do, what I do in Jedi 5 is, for example, in fun call will have execute, and fun call will also get type. And so I take this rule and I basically just try my best to translate that into Scala. That's the implementation of get type for fun call. Okay. Is this? Yeah, so you can see some examples of get types here. See if there are any interesting. Here's fun call, here's get type, and here's where I've translated that rule into, so I've done all of these things here. Well, no, I didn't do variable, but here's where I'm showing how to implement get type for some of these things. Come on, get back there, went too far. Now, so type checking is useful, of course, because it turns your type errors into compile time errors rather than runtime errors. But it's more than that. Really, the key to the power behind object-oriented languages and the power behind functional programming languages is the ability to create interesting types and define interesting relationships between them. Okay, so this notation here is used in Scala and also used in research to indicate, so here S and T are types. It indicates that S is a subtype of T. Okay, so S is a subtype of T. And it means a little bit different than subset. What this means, S is a subtype of T, is that members of S can substitute for members of T. And masquerade. Here are some axioms. T is a subtype of itself. If T is a sub, this is a rule, another axiom. T is a subtype of S if T is a subtype of R and R is a subtype of S. So it's transitivity. Here's some more in Scala. Every type is a subtype of any. Nothing is a subtype of any type T. And then here, S is a subtype of T if S extends T. Okay, so in other words, when I define like a class fun call extends expression, then what that means is the fun call type extends. We could write it this way: S is fun call, T is expression, fun call is a subtype of T. Here's some axioms in Jedi. T is every type T is a subtype of value. Integer is a subtype of real. And subtype can be implemented, so these subtype rules could be implemented in the type class using a subtype function. This is true if this is a subtype of T. Okay. This is the rule of subsumption. So we have another function here, has type, that we could add. Okay, so an expression has type T, okay, is has type T, and that equals get type is a subtype of T. So has type is more general than get type, right? Has type detects, so an expression can have many types now, okay? The type that get type tells you, okay, as well as any super types of that. Right? And here is the subsumption rule. If X has type S in an environment E and V, if the type of X is T and T is a subtype of S. So that's the subsumption rule. And that's basically what we call polymorphism in object-oriented languages. Let's see, so I'm getting a question here. Is there a way to avoid typecasting in Scala for running a method if it's only implemented in a subtype? You have a phone call to execute, you run for closures. This is a Scala question. So from 10, let me see if I can understand the question. Typecasting in Scala for running a method. Values, execute, must be run for closures. Yeah, I guess I don't quite, I'm not sure I understand the question, Dan. Maybe you could rephrase it, or maybe you could do it. We could go off and you could explain that to me. Finally, so we have, so we could add polymorphic subtyping to Scala, just like we have in Jedi. And that's great because, it allows a lot of flexibility in a programming language. And when an expression can have many types, can be used in many different contexts. So you use that all of the time. That's what makes our program right? Because subtyping means I'm expecting expression, but you can give me a fun call, or you can give me a conjunction or something like that. Conjunction has type conjunction, but it also has type special form. It also has type expression. It also has type any. And then finally, I'll just mention generic types. Okay, so generic types are parameterized types. Here's some examples of parameterized types in this is a definition of a parameterized type in Scala. And then here we see various instantiations of that, where we specify what T is. And this is great too, because there are a lot of code is what we call type agnostic. Right? What does agnostic mean? It means, it means maybe type atheistic. It means you don't really care, if you don't really care about religion, like it's Hindu or, and I'm getting the wrong definition of it. You don't really care. Here, you don't really, this content, you don't really care about what type T is, right? So rather than have to define, several different classes here, message of int, message of string, I can define one class that has the type of the content as a parameter. Okay, so because we don't really care whether it's a string or an integer. And then when I specify T, we're getting the actual type. And one way to think about this is think about it this way: message is a function. And when you give it an input, which has to be a type, message is a function which maps types to types. So it's, up a level, it's the type level, not the value level. And so when you give it an input like string, it's going to output a brand new type, messages with content equal the string. Here we're calling the function again. Message with input int gives us a brand new function, a brand new type, brand new class message of int. Okay, and we can even do, wild and complicated stuff like this. So you can think of a generic type as a function which maps types to types, but it's a function which maps types to types, but it's also a function. And then the last thing here, I'm assuming I've got two classes in Scala, A and B, and look, they are exactly the same, except for the name of the class. And here's a function which expects an input of type A, and it basically computes z.x plus z.y. And then the question is, if I give add an instance of B as input, is that okay? In other words, B and A look the same. Should they be treated the same? Okay, are A and B equivalents? And there's two philosophies about the structural equivalence used by some languages that would say yes, because structurally they're the same. So we should be able to use B in there. And then name equivalents, no, simply because they have different names. And languages like Scala and Java use name equivalents. C supports structural equivalents, not for structs, okay, which is like classes in C. Okay, so that is your brief overview of type systems and what they might look like in Jedi 5, type inference. And let's see, I get this question again. All right, so let's see, maybe I understand this question better. So value as instance of closure applied to execute the closures apply method after checking if the value is a closure. But since funcall can take non-closure values, to cast as the subclass above to find the apply method. Let's see, maybe it'd be better, like just talk this through, but Ian, the iteration file you had up. Okay. Well, let me deal with Ian first here. So, Ian, if I understand what you're saying, let's see. I still have that. Here's the iteration shot file, but I'm going to. So, Ian, if I understand what you're saying, you've got something like this, right? You've got args is this is inside of this is in from. So you've got, we've got something like this where we're turning operands into values, arguments, right? And then you're going to be looking up the operator, right? If we'll execute the operator for the fun call like this, right? And maybe we do this. If this you're doing probably this. If dot contains then maybe you execute the operator and then say if it's not the case that v dot is instance closure, throw some kind of type exception. And otherwise, not, then you're going to do v dot, let's see, what's your code, as instance So is what you're asking is you'd like to avoid this cast? Is that what you're saying, Ian? Yes. And so what you would propose doing, you'd propose doing what? Propose doing something like that instead? Just do v dot apply. When you're casting is the only way. I think so, because, the only way around this would be if in your trait, something like this. For example, if you had apply in the value, a do nothing or a apply method that just did some silly thing, then then you could regard the apply method in closure as an override of that. Okay, and you would avoid having to do the cast here, but you do need to do this, because it's already got a definite because remember when you execute the operator, that produces some value, but that value could be a real number. That value could be, any kind of a crazy thing at all. And it might not make sense to apply a real number to a list of arguments, right? And so this type check right here is sort of like a cast, right? Could you cast V to a closure? And if you can't, then throw an exception. By the way, I'm not sure that throwing, you don't have to necessarily, this is like a debate here, right? If help, maybe you could help me out on this, we could take a little vote. If I do something like this, what should happen here? Okay, think about this for a second here. So I actually did kind of a dumb thing here. It looks like I redefined the add function. Okay, so when we come down in here, I'm going to say, does the environment contain add? And it'll say true, that it does contain add. Okay, and then I'll say, well, is add an instance of closure? Well, no, add is 2. And so then I get mad and I throw an exception. And furthermore, here, so that means we'll never get to the ALU executing. Right? So another way of doing this would be to do maybe this. maybe this would be a kinder, gentler way of doing it. You could say, and here's, you pass it on to the ALU. So here, I don't get mad if the operator is not a closure. I don't get mad and throw an exception. I just say, oh, okay, well, it wasn't a closure, so I can't help you out here. Just carry on, right? And so then we come down here to else, and we do this. And then what that would mean is that we were allowing this. So you could define something called add, you know, and you could still treat add like an ALU function. It doesn't ruin add. Could do this, or the other thing we could do, which we haven't done, is when you inside of declaration, you know, we could check to make sure that the thing that you're declaring isn't some identifier that's important to us. Okay, so here. Cassie, it's the only way to improve Jedi. We have to check predefined operands every time a define is ran. Yes, that is correct. So a feature to Jedi, would this be a good final exam question? Maybe. Is we have a rule, we had like a rule to Jedi saying reserved words and ALU functions, you're not allowed to redefine those things. And that rule would have to be enforced in declaration.executes. And then let's see, Mike, you wanted to see iteration again. Here's my iteration code. So how are we doing here? Any other questions? Be a good time to ask questions about tonight's homework. Okay, well, I am out of stuff to say. So, and class is close to the end here. So why don't we break off for now? And we'll have a Friday office hours. Oh, we have Thursday class, of course. Thursday we will do the final exam. Yeah. All right, I'll see you Thursday.